Hello, Algebra 2. Today we're going to look at solving matrix equations, and before we can do that, we need to figure out some basic details about what it is to be a matrix inverse. So, this is kind of one of the cumulative lessons of this unit. We've been building to this, so it's kind of the most important thing, pretty much, in the entire unit. Also pretty fun, I think. See if you guys agree. So, first thing, some square matrices have an inverse, and some don't. I guess I was feeling like one of those Mounds commercials today. Sometimes you feel like a nut. Sometimes you don't. So sometimes you have an inverse, sometimes you don't. What determines that? Well, we're going to build to that. And what is a matrix inverse? So I said inverses of matrices, the reason we need them is because we're going to be solving really basic matrix equations today. I think you'll see how this ties in with systems of equations very quickly here. So, what is it to be an inverse? Well, can you guys just tell me, first of all, how do you know this is a matrix equation? What tells you right away, even if I said that, if I just said nothing about matrices? If you know anything about math, you should look at that and be like, oh, it's matrices.
They're all capital letters.
They're all capital letters, exactly. Let's pretend it wasn't matrices. How would you solve for x? Because clearly you're probably trying to solve for x just like usual, except it's a matrix equation. How do you get x by itself? You guys know. Divide by a. Last week we discussed why dividing might be kind of a problem, right? If you have a matrix, there's different containers. Do you divide like some of those entries by some of the other entries? We learned how to multiply matrices, we learned how to add them and subtract them, but remember we learned one other thing about matrices that was big. What was it called last Thursday? There was scalar multiplying as well, you're right, Alicia. But we learned the big D, determinants. And if you remember, I said to think about determinants as kind of like matrix division. So I think we're going to learn exactly how that works today. So we want to do something kind of like divide by a. Think about that word inverse. What's the inverse of subtracting? Adding. What's the inverse of dividing? Multiplying. So inverses are kind of the way that you solve equations all the time. It's just that's a more general word for it. Here is the notation for inverse in general. And this is a notation that we definitely want to remember forever. If I want to get rid of a, and I can't divide it because matrices don't divide, I can still do the inverse, whatever that is. So this is the notation for matrix inverse. Superscript -1. Now you guys have been doing a lot of power table computations with me, right? Haven't we seen lots of negative exponents? What does a to the -1 really mean? It means 1 over a to the 1. So really, if you think about that, that's kind of like, even notationally, dividing, isn't it? Isn't this basically dividing by a on both sides? Yes. That's why the notation is like that. But this is the notation for inverse. So I'd, in your notes, say this is the notation for inverse. It's not going to change when we see other functions, other things. So if I do it on one side of an equation, I have to do it to the other side. So I'm going to do it to the other side. If you've got a pen, you might want to pause. I did it to the other side. Think back to what you know about matrix multiplication now. For regular numbers, it's okay to switch the order, right? Like 7 times 3 is 21. Just like 3 times 7, if I reverse the order, is 21. Was that the way that matrices always worked last week? Not at all, was it? In fact, were they ever like the same? I don't think we've ever done an example where when you did AB, it was the same as BA. It like never works that way. So what do I need to do? I can't really put this here. Where can I put it? If I did it on the left side there, I need to do it on the left side here, or I'll be wrong. Now, when you, of course, operate with the inverse on both sides, if it's truly the inverse, we're going to see what it means to be a matrix inverse here in a second. What happens to any inverse in A? They cancel out, and you get what you're supposed to get, the solution x. So in this case, they cancel out, and we get x equals A inverse times b. This is a holy grail thing you're going to want to remember for a long, long time. Use it in multiple other kinds of classes if you take them with me. Okay, so x equals a inverse b is going to be the solution to this super simple matrix equation we're going to use. So the question is, how do you find the inverse? What does it mean to be inverses to begin with? Let's investigate. So I'm going to leave that up, and here's our first example. We've got two candidate matrices. So my question is is T the inverse of R? Have a look at them. See if you think you can tell. They're really different, right? Do you think there's any way to look at them and just tell if they're inverses? Well, yeah, but you gotta be pretty good at this stuff. Gotta have a lot of experience. Even I, most of the time, can look at them and be like, it's possible? I don't really know. So the way that you might check is multiply them and see what happens. Let's just multiply these guys. Let's find the matrix product, RT, and just see what happens. We know how to multiply matrices. Let's do it. So I'm going to go R times T. Okay. Are we going to be able to multiply those? I guess I should ask myself that question first. Yes or no?
Yes.
Of course, because they're both 2 by 2s, so the answer is going to be a 2 by 2, right? We're going to have 4 blanks to fill in. Time for some finger action. Here we go. Negative 2/3, slide 5/3. I'm going to write this down. Negative 2/3 plus 5/3. That's what you get there, right? You have a nice common denominator. That's awesome. So I got 5 minus 2. 5 minus 2 is 3. What kind of things are they? Thirds. 3/3 is otherwise known as 1. I'm going to really use a special color for this just to be clear. Okay. I think we've got one other column to hit with that row. So 5/12 plus a negative 5/12. So I'm going to write that one down. It's not very exciting because 5/12 minus 5/12 is 0. There we go. I think we've hit both columns of the first row. Let's now do it with the second row. So what is this going to be? Help me. Help me, childrens. Negative 8/3. Slide. Oh, at 8/3. What's that come out to? 0. All right, we've got one last one to do. 4 times 5 is 20/12. Slide. Minus 8/12. 20 minus 8 is 12/12 is 1. That seems kind of special. Did you guys see some kind of like symmetry happening when we were doing that? There was some kind of symmetry happening. So I just want to talk a little bit more about the theory before we launch into the big gun stuff. Okay? Does that or does that not show if R and T are actually inverses? Of course it does. What does it mean to be an inverse? Well, if you have something like, let's go back to basic numbers, like 2, what is the multiplicative inverse of 2? 1/2. When those cancel out, you get 1. Let's go to just solving a really basic equation like this one, but with regular algebra. A really easy equation. How about 2x equals 6? How do you solve for x there? You divide by 2, right? You go like this, and you give x equals 3. So the point is not what you get, but what's left. 2 over 2 really creates what? Doesn't create 0, because then you'd have nothing, not x. How many x's are here? 1 x is here. So really, when you use something's inverse on itself, you're supposed to get 1 back. Is this 1? The answer is yes. What does 1 do in number land? Well, when you multiply stuff by 1, you get the stuff back. If you take 7 times 1, you get 7. If you take 2.7 times 1, you get 2.7. If you take negative 8 times 1, you get negative 8. 1 is the identity number. This is known as the identity matrix. If you don't believe me, experiment. When you multiply by the identity matrix, you're supposed to get yourself back. The crazy thing, well, I don't think it's that crazy, is that in matrix land it has to be different sizes to suit your problem. So how about we take the identity matrix and we'll multiply it by something completely random, and we should get that completely random thing back. Morgan, pick a number.
3.
Jacob, pick a number.
10.
Kaylee, number.
2.
You guys all like positive numbers. Alicia, pick a number.
4.
I'll make it negative. Doesn't matter what I put in here. If I do the multiplication, I should get that thing back. This is the matrix version of 1. If you multiply two matrices and you get the matrix version of 1, those matrices were in fact inverses, whether you realized that or not. Because multiply 3 plus nothing is 3. 10 plus nothing is 10. Nothing plus 2 is 2. Nothing plus -4 is -4. You guys see how I just copied that matrix? That means it is the same thing as 1 in matrix land. So I just showed you how to confirm that something is or is not the inverse of another matrix. Let's write down what that was. This little dude right here that we got is known as the identity matrix. I would write that in your notes. Identity. The identity matrix can of course be different sizes. If you have a 3 by 3, I looks like this. 1, 0, 0, 1. How would you get it to copy? You might have to think about it like this for a while. See, it's all about this move. Will this be a 0 or a 1?
Oh, I get what you're saying about
It's only got to copy one thing at a time. Everything has to be a 0 except the diagonal. If you want the 4 by 4 matrix version of 1, just put another 1 on the diagonal, fill it up with zeros. That is the identity matrix. So really over here, when we multiply the inverse times the matrix, what's still chilling here technically? That. The matrix 1. Now of course, since it's the matrix 1, when you multiply it by x, you still have x. So this is consistent with everything you've ever learned about numbers. It's just new. So we tested to see if r and t are in fact inverses. I didn't show you how to find one. Let me show you how to find one. Let's say C is our candidate matrix. We need to find its inverse. I'm going to try to pick something pretty simple. 1, 2, 3, 4. You know what? That sounds good. Should we make one of them negative? Let's make one of them negative.
-1.
You guys are thinking good. I'm going to go a little bit more. Let's say negative. Thinking simple. That's good. Okay, so how do you find the determinant? Here you go. Or how do you find the matrix inverse? Well, I told you last week determinant had something to do with it, right? So it's got a determinant in it. So C inverse is found by going 1 divided by its determinant. There's where the kind of division thing comes in. And then you scalar multiply that by a new version of C with some stuff switched around. You switch this and that. In other words, the first entry and the one in the bottom right corner.
top right.
And these do not move. They get negated. So you make them the opposite of what they were. Okay, now last week I think we figured out how to do the determinant, right? So let's do that, figure out what the determinant is. I'll do some scratch work. So what's -4 minus -6? There we go. I'm just going to copy and paste this dude right here. And distribute, because that's a scalar, right? It's just a number times a matrix. So what is a tenth or -1/10 times 4? Negative 4. It's positive, right?
Yeah, so
4/10. Negative 1/10 times negative 2 is positive 2/10. Positive 3/10. Negative 1/10. Now, of course, I claim that this is the inverse of C. You guys might not believe me. How could you check?
plug it.
Multiply it by
Take this and multiply it by C, and you're supposed to get
The same.
identity.
the identity, the matrix version of 1. We have our calculator. Instead of doing that the long way, let's just use our calculator and see if we can get it. So I'm going to write these down next to each other for anyone watching the video. So C inverse, we came out with 0.4, 0.2, 0.3, and negative 0.1. So we'll multiply those together really quick and see if we're correct. I think we're correct, but maybe we made a mistake. So, just like last time, need to go over to edit, right? I've got a 2 by 2, and I'm going to load it up. Okay, there is matrix C. And now I'm going to quit and go and load up matrix, the other one. 0.4, 0.2. If you want to type in 3/10, you of course can. It'll work just as easily. And I'll go to the home screen and multiply them. So go and grab matrix A, multiply it by matrix B, and you can see that they are in fact inverses because I get the identity. Cool. All right, why have we been doing this again? This almost deserves a drum roll. Let's have a look at that. So in the next video, if you've been watching this one, we're going to get to one of the greatest things I think you've ever learned in math so far. How do matrix equations relate to systems of equations? I'll see you then.